For these examples, we're going to think about changing magnetic flux, and we're going to draw the induced field and the induced current. We'll do this by applying Lenz's law in each case. So that's what we're going to do next. So for our first one, we're taking a magnet and we're pushing the north end of it up towards a loop of conducting wire. So this is a conductor. So let's ask what happens, and then we'll start to apply Lenz's law. First thing we'll remember is that the magnetic field coming out of a bar magnet comes out of a north pole. So the magnetic field coming out of that magnet is coming out of the north. So I grabbed a little bracelet. So the magnetic field is coming up this way. So there's the back, there's the front. It comes up this way. We're pushing the magnet in closer, so the magnetic field is getting stronger. So we're increasing the upward field through the loop. And I think this is probably the only time I'm going to write all this stuff down. You guys can go through and you can make your own notes as you go. So if the field that points upward through the loop gets bigger, Lenz's law says there will always be an induced field to oppose the change that we make. We're making the field that points up bigger. So, and here's where you have to hit pause and decide which way you think the field is. So you have to hit pause and draw it on your paper. Okay, so now I'll assume you're back now. So we've made the field bigger upwards. The induced field then has to point down. That's the only way to oppose that increase, is to make a decreasing field. So our induced field is going to point down through the loop. So therefore, induced field is down. So now we have to take the idea of that induced field and ask, can we find the direction of the current? So here's my loop. Let's just turn it a good bit. So the induced field is down. My fingers make so my thumb curls with current. My thumb points with current. My curled fingers show the magnetic field. I'm putting my curled fingers through the center of the loop, and they're pointing down because the magnetic field is down. We ask, what's happening to the current? Well, it's pointing to the left along the front. So the induced current is to the left along the front. There's your induced current. And if it's coming back this way in the front, it swings around this way in the back. So the induced current is left in the front. Okay, and we figured that out just by thinking about Lenz's law. In the next, we have our bar magnet, but this time we're moving the loop. So we have our bar magnet. It makes the magnetic field that points up out of the north. So something like this. This time, instead of moving the magnet, we're moving the loop. Okay, so here's where you should hit pause and you should try and figure it out yourself. What do you think happens? So there's the magnetic field. It points up through the loop. I move the loop away, so I'm weakening the amount of field. As I get further away from that bar magnet, the field gets weaker. So the amount of field that points up is weaker. I need to induce, or nature will induce, a new field that points upwards so it doesn't get weaker. So the induced field will be like this. And if this is my induced field, I want to get my induced current. So here's my loop. My induced field is up. We ask, what is my thumb doing? So pointing upwards through the center. In the front of the loop, it's moving to the right. And in the back, it will move to the left. So the direction of my current is to the right in the front, and will come around to the left in the back. So we'll label this I induced and B induced. The next one, what if we have a conducting loop and we allow it to fall into a constant magnetic field? Okay, I could draw on this, but it'll get a little bit cramped, so I'm just going to scribble on some fresh paper. So our falling is going to happen in 3 steps. First, the loop is completely outside. If it's not in an area of magnetic field, nothing happens. Then it falls partly into the loop. So it falls in a little bit, so the front edge is in, the rest is out. Then it will fall completely within the loop, within the field for a while. So from here to here, it's completely in the field. Then it starts to fall out of the field. So this is going to happen in 3 steps. Let's look at each of those 3 steps. So first, as the loop falls into the field, so the leading edge is in the field, the trailing edge is not in the field at all. Okay, so here's a good spot for you to hit pause and ask if you think you know what happens, and then come back after you write it down. So the loop goes from an area where there's 0 magnetic field to a place where there's magnetic field that points into the page. Our loop needs to oppose that. How do you oppose a field that increases into the page? Well, you create a field that comes out of the page. So the induced field has to point out of the page. So now the next thing we have to do is ask what current is associated with that field. So let's look at the bottom part of our loop. I'll just use my round bracelet. The induced field is out of the page, so on the bottom part of the loop, the current travels to the right. So then it would go up here, and this would be your induced current. So that would travel counterclockwise. Okay, so the B induced was out of the page because we put it into an area where the field was into the page. So it went from nothing to into the page. To oppose that, we want to have nothing. The way you get nothing is you make one that opposes the field you have. It has to come out of the page. Okay, the next phase is it's falling, but it's completely within the field all the time. Okay, now you hit pause, see if you know what the answer is, then you come on back. So in this situation, there is no change in the magnetic field. It's falling in an area where the field is the same and it points into the page. So there's no change in the area, there's no change in the field, there's no change in flux, so there's no induced magnetic field or current. Okay, so the current turns on counterclockwise as it enters the field. The current turns off as it's falling within the field. Last step is it falls out of the field. Let's see what happens that time. So as it falls out of the field, the leading edge is now down where there's an area with no magnetic field. The trailing edge is in the area where there's still magnetic field. So here's where you hit pause and go try it yourself. Then you come on back. So as it goes from here to here, here it has lots of field into the page. Here it has not very much field into the page. So the induced field wants to maintain what it had here, which was a big field into the page. So the induced field is going to have to be into the page to make up for the fact that this stuff has none into the page. So there's our B induced. And then for our induced current, let's use our right-hand rule. The induced field is into the page. So on the bottom, my thumb represents my current, which comes around to the left, and in general, the current comes around clockwise. So now the current in the loop looks like this, and I induced is clockwise. Okay, one more set of examples, and then we'll be able to move on to Faraday's law, which lets us put some numbers with this stuff. So in this next example, the current in the wire is decreasing. So we have a straight wire here, the current is decreasing. This is a little bit like the example we did in one of the previous videos where we thought about this current and we calculated the flux here. Now we're going to say that this current is changing. What current is induced in the loop? So let's ask what happens because of this wire. So this wire has a current that points this way. Our magnetic field is going to be big circles around the wire. What's the direction right here? Well, the direction right there is into the page. So the magnetic field, where the loop is, points into the page. So there's B due to the wire. Well, what happens with this B due to the wire, we know that B is mu naught I over 2 pi r. The current is decreasing, so the B in the wire decreases. Well, what happens if the B decreases? The induced field will oppose that change, so if the into the field is getting weaker, the induced field will have to also be into the page so that it doesn't get weaker. So our B induced is also into the page to oppose that change. What does that give us for current? Well, if our fingers go into the page, we see that our thumb comes around in a clockwise direction. So our induced current comes around this way. So what current is induced in the loop? Clockwise. Okay, after we get done with Faraday's law, we would be able to calculate the magnitude of that, but for right now we're looking at direction. Next, immediately after the switch is closed, does the lower loop exert a force on the upper loop? So let's ask what happens in this circuit as we go along. When we close the switch, the current flows from positive to negative. So current is going to flow this way. Switch is closed. So this is the back of our loop. This is the front of the loop. The current comes around in the back like this and towards the right in the front. So in the bottom, the current is flowing this way. Well, if the current is flowing, this is a current loop. We know that current loops make magnetic fields. And the direction of that magnetic field, the current comes around like this. The direction of the field is going to point up. So this loop is going to make a field that points up. Okay, so there's our magnetic field. So we close the switch, we turned on the current, that created the field that pointed up. So now we ask, what happens in this upper loop? So if all of a sudden a magnetic field pointing up occurs, well, there's going to be an induced field that points down. So there's our B induced. And you might wonder why we're trying to figure this out, because ultimately we know that there is a force between two current carrying wires. So we're trying to sort out what's going to be the current in this wire. Okay, so we close the switch, we turn on the current. Turning on the current gives us a current that points around this way, which makes a magnetic field that points up. To oppose the field pointing up, we get an induced field that points down. An induced field that points down gives us a current that goes towards the left in the front. So our induced current will come around towards the left in the front, towards the right in the back. There's our I induced. So it makes a current that flows in the opposite direction. So what we have are two wires with opposite currents. And we know that two wires carrying opposite currents repel. We did that when we looked at forces in current carrying wires. Therefore, the answer to our question is yes. Okay, last one, and we won't fully answer this question just yet. The question says, what is the induced EMF, and we know that means potential, around this loop? We can't answer that quantitatively until we get done with Faraday's law, but let's answer the part about the direction of the induced current just yet. So our magnetic field points out of the page. If we look at our graph, we see that the magnetic field gets bigger as a function of time. It starts as 0 and it gets bigger. So our magnetic field, we're making a change where it's bigger out of the page. The induced field then will be into the page to oppose that increasing field out of page. If the induced field is out of the page, what that gives us for a direction of current is clockwise. So our induced current will come around this way. After we get done with Faraday's law, we can come back and do this afterwards. Oh my goodness, I got a whole left-right thing. It's terrible. Our magnetic field induced is into the page, and then our current comes around clockwise. Not entirely sure what I said or did before. So the B is your curled fingers going into the page. Your thumb is your current. We see it in the bottom part of that loop that goes to the left, goes up on the side, and goes to the right on top. So there's the direction of our induced current. Okay, and then after we get done Faraday's law, we can come back and see how big the induced EMF and the currents actually are.